Welcome back everyone, I am Shaptaporni from BioLife. Hope all of you are doing very well. So in today's video, we are going to discuss about the change in gene frequency or allele frequency within a population due to mutation. And we are particularly going to discuss about change from dominant to recessive trait. Okay, see, if there is a population in Hardy Weinberg Equillibrium, then for a given locus within that population, the gene frequency or allele frequency and genotypic frequency remains constant or unchanged generation after generation if no evolutionary force is acting on them. But if any kind of evolutionary force is acting on them, like mutation, which is an evolutionary force, then we can see there is a change in gene frequency generation after generation due to that evolutionary force or here the mutation. Okay, so here we are going to see that if there is a change from dominant allele to recessive allele for a given locus within a population, how gene frequency is getting changed generation after generation in a population that was first in a Hardy Weinberg equilibrium. Okay, so before going into that, we must know what is mutation. See, we all know that mutation is a heritable change that can convert one allele into another for a given locus and thus can alter the gene frequency within a population. Okay. Now, we must remember that the rate at which the mutation arises is very, very low. Okay, it is generally 1 into 10 to the power minus 5 to 1 into 10 to the power minus 8 per generation. That means if there are 1 lakh or 10 to the power 5 capital A allele, okay, in a generation for a given population, then only one of them can get changed into a small a in a single generation. Okay, so you can see how much less is that. Okay, you can imagine that. Now, you must also remember that this rate is not constant for every locus or for every species. This can vary between locus and species. Okay, now there are two terms, forward mutation and reverse mutation. Forward mutation is that when for a given locus dominant allele is getting changed into recessive allele, that kind of mutation is known as forward mutation. Okay, and at which rate that mutation occurs? U rate, and that rate is known as forward mutation rate. On the other hand, if the recessive allele is getting changed into the dominant allele, then that type of mutation is known as reverse mutation, and the rate at which that mutation occurs, that means the small v, is known as reverse mutation rate. Now, we must always remember that forward mutation rate is always much greater than reverse mutation rate. That is why during our mathematical procedure, we can neglect this reverse mutation rate because it is very less. Okay. Now see, there could be three types of mutations depending on the environment. Okay, it could be neutral or detrimental, that means negative mutation or bad mutation, and advantageous or good mutation. From the name, you can assume that in case of neutral mutation, these type of mutation do not affect the reproductive fitness of an organism, okay, within a population. Whereas in case of detrimental mutation, that is majority in number, okay, that eventually gets eliminated from the population. Why gets eliminated? Because when any individual possesses this kind of negative mutation or detrimental mutation, then its chance of survival or chance of reproduction gets decreased day after day. Okay, that is why its frequency gets eliminated from the population, or its frequency gets decreased and ultimately eliminated from the population. Okay. On the other hand, there are some advantageous mutation, very less in number, but this kind of mutation actually convey some good adaptive trait to those individuals who possess them. That is why it spread through the population generation after generation. Okay. Now, let's see in a population which is already in Hardy Weinberg equilibrium, how the change from dominant allele to recessive allele for a given loci or given locus changes the gene frequency of the dominant allele generation after generation. Okay, so let's assume for a given locus there are two alleles, capital A and small a, within a population where capital A is dominant over small a. Okay, so say at a particular generation, that is G0 generation, U proportion of all the capital A alleles is getting changed into or getting mutated into small a. And at that generation, the allele frequency of capital A is P0. Okay. So in the next generation, in the G1 generation, after the U proportion of capital A got mutated to small a, the new allele frequency for capital A becomes P1. So P1 equal to P0 minus UP0. Why? Because P1 is the allele frequency of capital A in the G1 generation. That is equal to the allele frequency of capital A in the last generation, that means in the G0 generation, minus the proportion of capital A allele that got changed into small a multiplied by the frequency at G0 generation for capital A allele. Okay. So you can see here the formula becomes P0 into 1 minus U. That means the frequency of capital A allele is getting decreased by UP0 in the first generation. Okay, you can see that clearly here. So frequency of capital A is getting decreased as some of the capital A is getting mutated to small a. Okay. Now similarly, if we go for the G2 generation, then we can see that again U proportion of the remaining capital A allele is getting converted to small a, and thus the new frequency of capital A in G2 generation becomes P2. Hence P2 equal to P1 minus UP1. Okay, because U proportion of the remaining capital A allele in the G1 generation is getting mutated to small a allele. That is why UP1 is getting subtracted from P1. Okay, hence the formula becomes P1 into 1 minus U. Now we can replace P1 with P0 into 1 minus U, and hence the formula becomes P0 into 1 minus U square. So we can see here the generation time is getting at the power. Okay. So hence at the tth generation, that means GT, the allele frequency of capital A becomes PT, which is equal to P0 into 1 minus U to the power T. Okay. So using this formula, you can get the allele frequency of the dominant allele at any generation, and you can also get the mutation rate if you know the generation number and the allele frequencies in the earliest generation and at the tth generation. You can also get the forward mutation rate. Okay. So from this we can clearly see that as the generation increases, the PT approaches 0, because in every generation some proportion of capital A is getting converted to small a allele. That means the portion of capital A is getting gradually decreased, or its frequency is gradually decreasing generation after generation, whereas the portion of small a is getting gradually increased. Okay, hence after many generations, capital A will be completely abolished from the population and small a allele will be gradually increasing and becoming the only allele to exist for the given locus in the population. Okay, so that is how the gene frequency or allele frequency gets changed when in a population in Hardy Weinberg equilibrium faces evolutionary forces like mutation. Okay, here the forward mutation. So I hope this video is useful for you. If you find this video useful, don't forget to hit the like button and share it with your friends, and don't forget to subscribe to my channel for more such videos. Thanks for watching and happy learning.